Hello, everyone. Today we're going to be learning about the Metropolis algorithm. The Metropolis algorithm is a type of Markov chain Monte Carlo method. All right, so what's the motivation here? So let's go through the outline first. So we got the motivation. Then we're going to talk about the methodology. Then we're going to talk about the Markov process. And we'll talk about the stationary distribution of that Markov process. All right, so let's talk about the motivation here. So we know in Bayesian statistics, many times we know the likelihood and we know the prior. But many times we don't know what this P of D is, which is the probability of the data. And it's very hard to compute this because this is the integral for it. And it's very hard to compute. And many times we can't compute it. So we must work around this by first we know something that's proportional because this P of D is just a normalizing constant. So we're trying to find a function that we're trying to find a density that from an unnormalized density that's proportional to it. So that's where the Metropolis algorithm comes in. And let's make some notation here. Let's make f of x be proportional to the unnormalized density, which is the likelihood times the prior, and let's let p of x be the target distribution, aka the posterior. So here's the methodology. The first step here is to pick a point, just an arbitrary point x sub t, and then next we're gonna sample from a jumping distribution, g of x given y, where y in this case is x sub t for the first iteration. It's gonna be centered at x sub t, and normally this is symmetric, but it doesn't have to be. But for our case, it is going to be. And the most common distribution that's symmetric is a normal distribution, so we're gonna use a normal distribution centered at x sub t for the first iteration. And then we're going to generate a sample from that called x prime. So we're going to sample from this normal distribution centered at x sub t here. And then we're going to set this new sample point if we plug in the respective x prime and x sub t into the proportional function, which through the mathematics, we can figure out that the proportional function is actually becoming the ratio of the posterior, because the normalizing constant cancels and when you take a ratio. So we're essentially accepting this new point with the if it's greater than one, if this ratio is greater than one, if the new point is it has more density under it than the last point. And I'll have a graph on the next slide explaining this. But if it's less than one, we accept it with the probability of the ratio. And then notice in this case we're always accepting if the ratio is greater than 1. That means we're moving towards the density of this distribution iteratively. Now let's look at an example of this. So we have x sub t here at the center. This is our point we just picked. And this red curve here is normal distribution centered at 10. And then we're doing a sample x prime, which is over here. It's this random sample. It's 8.5. And then we notice in the purple here, this is the proportional unnormalized density. And then we're just looking at the y values here. And then we're calculating this ratio. And if this ratio is greater than 1, aka there's more density under this part than this part, we're going to accept it all the time. And then if it's less than that, let's say if the point we're sampling from was 11.5, we would accept it with the ratio of this point divided by this point at the y value of this purple line. So we accept it. A property of the symmetric distributions. So a property of the symmetric distributions is that conditional symmetric distributions, for example, where x prime given x sub t. So example, the x sub t is this curve right here, centered at x sub t, and x prime sampled from it equals the purple curve here sampled at x sub t. So as we can see from this graph, these are equivalent, and that's a property of symmetric distributions that we will discuss later when we're trying to prove something about the stationary distribution. All right, so notice this is a Markov process. The sample of the next distribution depends on the sample of the present. And notice this Markov process has a continuous state space, which is not usually what we think of when we think of Markov processes. Usually when we think of Markov processes as we have a discrete state space. But that's not true here. So that means we cannot create a transition matrix, and we'll get to that in a second. The index set here is the number of iterations. Obviously, theoretically, that can go to infinity, but obviously in applications, we can't hit infinity, so it's like some arbitrarily big number. So since the jump is a symmetric jump in our case for the Metropolis algorithm. We're going right or left with a 50% probability. This is like a random walk with the chance of going right or left with a probability of 50%. We'll get into that when we're talking about the stationary distribution and proving the uniqueness of the stationary distribution. And like I said earlier, the transition matrix cannot be achieved because this is a continuous state space. So we have something called the joint transition kernel, or density. It's basically a joint density. And we're going to see that this joint density is actually independent and it's actually symmetric. So that's pretty cool. And I'll go into that later. But given a Markov chain is currently at state x, the last iteration, the next value will be drawn from a normal distribution centered at x t minus 1. That's what this transition matrix means. So let's go into the stationary distribution. Now we know Markov chains, a property that they have is sometimes they have a stationary distribution. And we're going to prove that this one is actually a unique stationary distribution. And we're going to also prove that the target, the thing it converges to is actually the target distribution or the posterior, which is in the Bayes rule is what we're solving for, that we don't know. So after what is called a burn-in period, notice it doesn't converge right away, right? After one iteration, it's most likely still going to be it's not going to resemble the posterior after one iteration, right? So we have this burn-in period where we sample for a period, and then we discard this burn-in period, and then it is as if we're sampling directly from the posterior. Now, let's recall the conditions of a Markov chain to have a unique stationary distribution. It must be irreducible, aperiodic, and positive recurrent. And we're going to prove this by the simple fact that this is an adaptation of the random walk. And we know the random walk is irreducible, aperiodic, and positive recurrent. And in addition, we must prove that the target distribution is the stationary distribution of the Markov chain. And the target distribution, we'll prove that in the next slide. Let me save that for later. So like I said earlier, we know that the random walk is aperiodic and positive recurrent, and then we know this is specifically a symmetric random walk in which the going right or left has a probability 50%. You know, and the normal distribution is symmetric, so going right, sampling from the right or the left is 50%, right? So it has one class, so it's irreducible. Given these three conditions, it's a unique stationary distribution. That's pretty important. That means if we find the stationary distribution, that is the only stationary distribution that there is. Okay, so let's prove that the target distribution is a stationary distribution. Now, I will admit, I have this later in the next slide. This proof assumes that we're starting at the target distribution, and we're proving that the next iteration is also from the target distribution by the symmetric joint distributions. So consider the transition density function, like I said. It looks like this. And let's assume that there's two possible outcomes of this Metropolis algorithm. It can sample a point that is p of x of b is greater than p of x of a, right? And that in this case, when we're sampling if we're going from a to b, that means we don't have to consider this ratio because it's always greater than 1, right? So we can reduce this transition density into two steps of the Metropolis algorithm. First, draw x of a from p of x. That's the first step. Next step, draw x of b from a jumping distribution centered at x of a, right? And that's it. That's the marginals of this density. And now we have the other situation. Let's consider a ratio. So we're moving away from the density. Where we have p of x of a over p of x of b, where p of x of a is less than p of x of b, right? Now, if we notice something about this, again, we have step 1, step 2, step 3. Step 1, draw a sample from x of b. Then we have draw the next sample from a jumping distribution centered at b, and then we have to accept it with the ratio of this. So it's 3 steps. That means but if we notice something here, this p of x of b cancels with this p of x of b. So this reduces down to this equation here. And if we know something about symmetric distributions, like I went over earlier, we can replace this x sub a with this x sub b, so it's symmetric. So then what do we have here? This means this jumping distribution, no, this density right here, it doesn't matter if we have x sub b or x sub a in here. It's always going to be the same marginals. And that's huge because that means this density, this transition kernel, is always symmetric. So we're going to see in the next slide, this is where the proof comes into play, because let's review what symmetric distributions are. So basically, if you have a random variable and this CDF here, we're going to replace it by PDF here, but a CDF that's x less than or equal to x, y less than or equal to y. If we replace the x's and the y's and it's still the same distribution, that means the marginals are the same. And so in our case, this is our transition kernel or transition density, and we can replace the x sub a with x sub b, and it's still the same thing, like we proved earlier. That means conclusion. The marginals are the same. Recall, what are the marginals? P of x and the jumping distribution. So basically, sampling from the jumping distribution is like sampling from the posterior distribution. That is a proof, and I will explain in the next slide why it's not, in my opinion, it's not complete, but that is why the last iteration and the next iteration has the same marginal distributions, and the P of x is the stationary distribution. Now, a note on the proof, again, it assumed that the chain is already at P of x at time t minus 1. I really wanted to find a proof that would explain how it converges to P of x. But as I kept reading more and more on this topic, it became apparent to me that it required a little bit more mathematics, measure theory in particular, and I'm just not at that point to understand this material. But there's a great paper on it called A Note on Metropolis Hastings Kernels for General State Spaces, and it goes pretty in depth on it, and it'd be a great read if anyone is curious on more about the convergence to the target. So it's by Tierney and Luke here, and I've linked it here. Another thing about this algorithm here is that it's really good in high dimensional spaces, which I didn't put in the slides because I ran out of time, but it's really good it's really good at handling high dimensional situations, which is why it's very popular. All right, these are my references. This book right here is amazing Bayesian book, and the wiki, and some math exchange questions to answer my questions. So thank you for your time, and I hope you learn more about this MCMC method. And it's also not just applied to Bayesian problems. Like anytime you have like a function, you want to find the density, the probability density of given a proportional normalized density, it can solve any one of those problems. So it's not just for Bayesian, but it's heavily used in Bayesian statistics. All right, thank you for your time, and see you later. Bye.